It's the physics behind, for example,
another
the reactions.
people
The
say
reaction, the actual change of
under
mass.
the ultimate question about
During
the
my father's course of 7 years,
about
which the book was put together.
Hi, I'm Maya Harris, and tonight in the Scholars Chair, a conversation with Dr. Cole Miller. He is a professor at the Department of Astronomy at the University of Maryland. And along with him in our Science Scholars Chair, contributor Mr. Race Dowling. At Focus, who is Sir Isaac Newton, and what is his contribution to astrophysics? Right here in the Scholars Chair.
Let the conditions of inequality that we suffered under, when we are the oppressor, the dominant class, let's not impose that injustice on the others.
Anybody think that you could have a just system without giving women their rights?
Everyone has an opinion, and we sit around the marketplace and talk about opinion, but what is true?
With the shareholder, their goal is similar to the business, to maximize profit.
That belief becomes a context for a development of knowledge.
Say physics is the DNA of technology because the rules for how you build new technology starts in physics.
Because Quran challenges the people. It's not only the people of the book, it challenges Muslims.
We say secular, they hear godless.
Right.
What was intended?
Watch the Scholars Chair every Monday night. And here is your host.
So thanks for coming back to us here at the Scholars Chair. Now, there's been a lot of attention to the reboot of Carl Sagan's miniseries, The Cosmos, on Fox, and it's hosted by astrophysicist Neil deGrasse Tyson. And one of the things that keeps coming to the fore in the show is that Neil deGrasse Tyson says that it is Sir Isaac Newton who made some of the world's greatest contributions to scientific knowledge. Cole, can you tell us, do you agree with this? Why or why not?
Oh, absolutely. Sir Isaac Newton is one of the greatest figures in the history of humanity, let alone science. And in a lot of ways, he was a transitional figure. He was somebody who actually spent an enormous amount of time on alchemy, which we don't consider science today. But I think one of his most profound contributions is in unifying the science of the earth with the science of the heavens. Prior to him, most people looked at these as entirely different realms, but he showed that by studies here on earth, we can have profound understanding of the heavens. And this is really something that gives us a deep connection to the universe that in many ways was lacking prior to his contributions.
So, in one of the disciplines that we understand, when you talk about the heavens and his contributions to understanding the earth and relationship to the heavens, is astrophysics. So, what are some specifics that are contributions that Isaac Newton made that without which we couldn't have the study of astrophysics?
One of the big contributions is that he took what had essentially been empirical laws of planetary motion discovered earlier by Johannes Kepler, and he put them on a mathematical basis and allowed people to extend and generalize them, ultimately leading to the discovery, for example, of the planet Neptune. So this really gave people a context in which to put things as opposed to simply the happenstance laws that might have occurred before then.
Mm-hmm. That's very interesting. But it's not just astrophysics. We also know that Sir Isaac Newton, his discoveries actually contributed a lot to the study of light and our understanding of light. Race, you study photonics. That's your discipline of study.
Yes.
Can you talk about Isaac Newton's discoveries with regard to the laws governing light a little bit?
Okay. Isaac Newton, his forte was being able to think of things theoretically and at the same time be able to do physical experimentation. So he did a lot of work with prisms, and he actually measured the angles of various colors as they came out of the prism and how light moves and changes with medium, and made a lot of those calculations and then came up with things that are validating his own theories or used as being able to develop further theories. He basically discovered the reflection of light, where the reflection is selective absorption of various colors, and light doesn't shine out of your eyes. It basically your eyes receive light, and when it reflects off of, like, say, your red jacket there, it's selectively absorbing the other colors and allowing red to be able to reflect back. He discovered things like that. His theory, when he got done, he came up with a theory that light was composed of tiny particles, which was antithetical to the wave nature of light, which some of the other people who were in power at the time wanted, and led into some really big arguments. And he eventually had to publish, after the death of Hooke and some other people, to actually have his theory come out, the particle nature of light.
Okay, so that's interesting. So you say that there was a little contention. Who was Hooke, and what was his relationship to Sir Isaac Newton?
He was one of the powerful scientists. I believe he was in the Royal Society. I could be mistaken on that. Please correct me if I'm wrong. But I'm sorry, what?
That's right.
Yeah, he was in the Royal Society, so he had the power, and Newton was kind of a mean guy who wanted to be by himself and just sort of do things. In order for Newton to get things done, he had to actually work with people he didn't want to work with. And so, like, there's politics now, there's politics back then, there's always been politics. And he didn't really have much of a taste for the politics. So he didn't play ball with a lot of people. So he actually had to wait for people to die before he published things because he just didn't want to deal with them.
Oh, wow. But because he was able to work with them, and that's one of the things about both of your disciplines, whether it's photonics or astrophysics, you have to build on the discoveries of scientists that have come before you. So did Isaac Newton do that when did he discover calculus, for example? That's something that's out there, that he discovered calculus. Or is there a longer, deeper story to that?
There is. One of Newton's famous statements is that if I have seen farther than others, it is by standing on the shoulders of giants. And it's true. So, for example, the study of light, which Race was just discussing, there was an Islamic scholar named Ibn al-Haytham who actually had discovered in the 900s and 1000s a lot of the principles of light. And Newton came up with his understanding, which improved on that previous understanding, and then the centuries since have led to yet further advancements. In the case of calculus, many of the ideas were there in place, sometimes many centuries before. For example, the famous Greek scientist Archimedes came up with many of the principles that would later be used by Newton and others. Also, there was a contemporary of Newton named Gottfried Leibniz who independently came up with calculus. But these were still monumental and very important advances. They weren't small advances, but they didn't come in a vacuum either.
So going back to the study of photonics and Newton's contributions to that study, how are some of those principles applied today?
Oh, they're applied everywhere. Reflecting telescopes, various ways in which we can view spectra. All those things came out of Newton.
So that's, and I understand that in 1668, Sir Isaac Newton developed a telescope. How is his telescope different than the ones that came before, and how has it contributed to us having better telescopes now?
Okay, well, back when they started when optics was sort of invented and developed, it's long been known that if you shine a light through a piece of glass that's curved a certain way, it will break up into colors. It was looked at as a nuisance. And so a lot of the technology at the time was trying to find mixtures of glass that minimized that level of what we now know as chromatic aberration, but really is just like the lens acting like a prism and breaking up the colors in the light. So you have that and some other aberrations, which are in your standard glass telescopes. Also, when you use glass, it absorbs light. So if you're looking at things that are very faint, it becomes more and more difficult to see because it's like putting sunglasses in front of your eyes to some extent, because the glass always absorbs some and you don't get the full amount through. Now, the difference is that you can use a curved piece of glass, you can also use a curved piece of metal. And that will also focus light beams based on the focal length of the curvature of that piece of metal. Problem is, it focuses back on itself. So if you actually wanted to put your eye on the focal point to see the image, you'd block the light coming in. So that makes it kind of impossible. It's not obvious to most people if you look at that it actually has a focal point and it would work that way, but in theory it's supposed to work that way. Okay. So what he did was he decided to put a small mirror on the focal point that shone the image out the side of the tube of the telescope. And by doing that, he could actually view the image at the focal length of the telescope. The good part about it is because you're not going through an air to glass to air boundary, which causes a chromatic aberration. You're going from air back to air, so it has no chromatic aberration. And that really improved the design of telescopes, and it's really the most common design today in telescopes. All of your observatories, with few exceptions, all have reflector telescopes.
So we're able, because of some of the discoveries of Newton and those that built upon his discoveries, to see further and further into the universe, correct?
Right. Mm-hmm.
Okay.
He also knew that he needed to, not only did he know that the reflector would work, he knew he needed to make it into the shape of a parabola, but he couldn't do it. So he just made it circular because that's all the technology would allow him to do. Mm-hmm. But he did a good enough job that he was getting very good results from it, even though he knew it was not completely correct.
So, but at the time, that was the best he had, and
Right.
people were able to build on his research.
Right.
So, and that's actually something going back to the ideas expressed by Neil deGrasse Tyson. So Newton was able to look at shine light through a prism, but one of the steps that he didn't take was refracting that light even further to see, and once that was done by later scientists, you could see the black spaces in between each color in the spectrum. What do those black spaces represent?
Every chemical element has a fingerprint based on absorption lines, which is caused by the absorption of photons to make electrons jump into different orbitals. Mm-hmm. So hydrogen has one electron, and it has certain fingerprint of those spectral lines. And because that particular wavelength is being absorbed by the electron, it doesn't emit. So it comes out as black because you don't see it. Mm-hmm. Okay, and basically that's what it is. It's a little more complicated than that, but that's pretty much it.
For me, that's...
They all have their fingerprint, and so by looking at the spectrum alone, you can tell what element was shining at the time.
So because we know that now, we can look through telescopes that look deep into the universe and tell what elements are in different solar systems.
It was essentially
correct?
Proof that the same elements that are here on Earth are present out in the heavens.
Oh, that's amazing.
And that was something that was contentious at the time.
Okay. So we have Newton contributing to our telescopes, our ability to see into the reaches of space, but also, I mean, he's famous for his discovery or outlining the universal laws of motion.
Right.
Cole, so can you tell us about what are they, and what about for the layman? Can you describe what they are?
Okay, sure. So the first law of motion is that an object at rest remains at rest, and an object in uniform straight line motion stays that way unless there's a force applied to it. Now, prior to that, people had seen that things slow down, and they imagined that was the natural state of motion. But Newton, and actually Galileo before him, realized that the little irregularities, the bumps, the friction on a surface are what are actually slowing things down, rather than this being a natural state of motion. The second law is in some sense a generalization of that, and it says that force equals mass times acceleration. So if you apply a certain force to something with a given mass, you can figure out the acceleration, which is the rate of change of its velocity. And then the third one is for every action, there's an equal and opposite reaction. Or you push me, I push you back. So, these laws of motion are things that are truly universal, and from them you can derive the full richness of phenomena that were known from classical physics.
Mm-hmm. And so before there was this understanding of these laws, some things that were natural phenomena that were occurring over a regular period of time were thought to be signs of cataclysmic events, right? Like a comet. But I think we talked a little bit about Halley's Comet and its regular rotation around the Earth is like 76 years. And that is, it's able to be calculated specifically because of Newton, correct?
Right. So Edmund Halley, who was Newton's great friend and actually shelled out his own money to publish Newton's masterpiece, the Principia, realized that there had been reports of comets at this 76-year interval. And because of the understanding that this was a natural and periodic phenomena, he was able to predict its next appearance. I actually was lucky enough to see its last appearance in 1986, going out into the freezing desert of California, but I wanted to say I'd done it. It's part of my life list.
I think that's one on a lot of people's life lists, but it's amazing that we're able to calculate that because of Newton. And another thing that we're able to look at and understand because of Sir Isaac Newton is the law of gravitation, universal law of gravitation. Can you explain that a little bit?
Sure. This is one of these things which really brings together an enormous number of apparently different phenomena. Things like apples falling onto unsuspecting physicists' heads and the moon orbiting the Earth, which Newton was able to understand as part of a universal and mutual law of gravitation. Essentially, the gravitational force that you put into Newton's second law is something where the force is proportional to each of the two masses, so your mass, my mass, in the same way, and inversely proportional to the square of the distance between them. And it's opposite and fully attractive. So in other words, I'm exerting gravity to pull you to me, you are exerting gravity to pull me to you. This is, in the Newtonian idea, something that applies to everything in the entire universe. So the Earth has a gravity on us, the Sun has gravity on the Earth and us, and this is something that he was able to use to figure out in a simple way a lot of these phenomena that people had thought were very distinct.
So can you explain, for example, I think what interests me is how gravity is different on different planets, and that's because of the different mass.
Yeah.
Explain a little bit about that for me.
So because the universal law says you have gravitational force which is proportional to the two masses, if you are a given distance from a very light thing, you have a very small gravitational pull. If you're that same distance from a very heavy thing, then you have a tremendous gravitational pull. And in fact, in the extreme and beyond Newton, we get to the idea of things like black holes, which are the ultimate victory of gravity.
Okay. So, and what is a black hole?
So a black hole is something which is what happens when gravity has pulled in all of the stuff and has left basically a hole. There's no surface like on this table. If you were to fall into a black hole, there would be a point of no return, such that no matter how you tried, nothing could get out, not even light. And this, as I say, in our modern understanding, is a little bit beyond what Newton had in mind, but the seeds are there.
So, Race, thinking about black holes and the study of photonics, I was speaking a little bit of how telescopes let us see deeper and deeper into the universe because of the light that we see, but is the absence of light also something that lets us know what's out there?
Oh, absolutely. It lets us know when there's dust and gas in the way. Things that are not luminous are things that are out there and can only be seen by the fact that stars get occluded by a lot of these things.
So would you be able to detect a black hole because of the absence of light, or?
No, we detect a black hole by its effect on the bodies around it.
Okay.
So it's gravity runs the cosmos. It's the weakest of all the forces. There's gravity between you and me. We don't feel it because it's very weak. But when you're talking about massive objects, gravity becomes the determining factor.
So when we look out into the cosmos, when we look out, and what does the lights that we see from the various stars, do they tell us anything about the distance of a star from us?
Well, we talked about the spectra again, which, by the way, is something Newton missed because he was probably too busy trying to reconcile Greek mythology with the Bible. Otherwise, he would have come up with it 150 years before we did, probably. But as said before, each one of those elements is a signature. So hydrogen has a certain signature. And it's not the position on the spectrum, it's the relative positions of the various black bars. Okay, so you can get hydrogen, you can overlap that with helium, you can overlap that with carbon. All these elements have different fingerprints. So if you have the fingerprint in a certain way, it gets shifted because of the Doppler effect. As things move away more faster, they get shifted more and more toward the red. You heard the red shift. which
Okay.
shifts toward the red end of the spectrum when it's moving away, and it shifts toward the blue end of the spectrum when it's coming toward you. So by looking at those fingerprints and seeing how they've moved relative left or right to the position on the spectrum, you can tell how far away something is moving away, how fast something is moving away from you or moving closer to you.
So does that contribute to our understanding of the universe's expansion, or how?
Absolutely.
Okay.
Yeah.
Okay.
Yeah, we determined a lot of things by that. We've even determined that the universe is accelerating now, which is something that just came out, a couple of years ago. Which means eventually we won't be able to see the stars that we see in the sky now, and if they're in different galaxies, we'll only be able to see the stars in our own galaxy. So the Andromeda Galaxy, all these other galaxies will be going away. We'll look like we're the only galaxy in the entire universe.
But that's billions of years away. Is
Yes,
that soon?
a long, long time ago. Long time ago. The Earth is probably not going to be here by the time that happens.
Oh, wow.
So,
that's too bad for us. No.
When you get back to the laws of motion, there's a lot of, you shouldn't be daunted by it. I mean, the three laws of motion is really very simple. The first law of motion is the reason why when you pitch a baseball, it keeps going. Mm-hmm. Okay, that's the first law.
Okay.
The second law is F equals mv, which means that F equals ma. I've made that mistake before, and it's just something that is ma, which just means that if you want to roll a bowling ball or a soccer ball, it takes a whole lot more strength to roll that bowling ball the same distance as it does a soccer ball. That's all that means. And the third one is action and reaction, which is why when you shoot a rifle, there's a recoil. Mm-hmm. And if you change to a larger cartridge, it's more of a recoil because it's pushing back on you. And that's actually, if you left the rifle by itself, it would go a whole lot further back and the bullet wouldn't go as far. But since you're stopping it with your body, the bullet actually moves further.
Okay. So those were great examples, real-world examples of how we can apply the universal laws of motion to our everyday life and our everyday experiences. What about the laws governing light? Can you give us some everyday ways that they're applied?
Well, okay. Inverse square law is gravity, light, sound. Everything follows the inverse square law because it's based on the geometry of the sphere. Mm-hmm. As you move further away from the source, energy can't be created or destroyed, which we know. Mm-hmm. So when you move further away from the source of the energy, it's covering a larger area. So if it was the same intensity of that area, then energy would have to be created from nothing. But it can't be created from nothing because you can't create it. So therefore, it has to be a loss in intensity at that point because that same piece of energy is covering a larger area. And it's just how the sphere works, which is why we get the inverse square law. Same thing with light. We're seeing these lights in the studio coming in, and they follow the same things that we do, that gravity does, only to varying degree.
Okay, so the light's something further away is diffused. For the light source is diffused as we get further and further away.
The same luminous body, two identical luminous bodies. Mm-hmm. One would be brighter if it's closer to you. If we brought the lights in closer to you, you would be a lot brighter. Bring it further away, you'd be a lot dimmer.
So we definitely need those laws when we prepare for the Scholars Chair.
Yeah, you also see, if you notice the street lights at night, the sodium vapor. Remember we talked about the absorption lines. The reason why they're yellow is because of those absorption lines. Okay. And if you have a nice colorful car, mm-hmm. right, and you look at it in the sunlight, it looks like one color, and you bring in a sodium vapor, it looks like a completely different color. That's called metamerism, and color science is one of the things that you have to worry about when you're doing things like Landsat photography and things like that.
Mm-hmm. And those are definitely real-world applications of those laws. So thinking back to Isaac Newton and his contributions, Cole, what would you say if you had to find a book that would tell you about Isaac Newton that isn't as complicated as the Principia, that the layman can learn something from and take something away from? What book would you suggest?
A book that I have not read, but I have seen a lot of very positive reviews, and I think the author is excellent, is simply called Isaac Newton, and the author's name is James Gleick. So he also wrote a biography of Richard Feynman, which I have and I love. And the indication is that this is a wonderful introduction to the man, the science, the times, which sounds like just what you would want.
And that's interesting, the man and the science. We talked a little bit about his dispute with Hooke, but also he had interests other than the science that we've built on. Can you talk a little bit about those mercurial interests?
Sure. Yeah, he was really into alchemy, like many people at the time, and it wasn't crazy at the time. He thought there might be some magical formula for turning lead into gold and becoming rich temporarily until gold was devalued. So he was really into that. And some people think that, in fact, some of his paranoia in later life might have been because he used mercury a lot. He was into biblical interpretation and end-of-the-world type prophecies. And he was also, for a significant time at the end of his life, commissioner of the mint, which meant that he was in charge of trying to foil counterfeiters, and he introduced ridges at the ends of coins, which make it tougher to file off. And so he actually sent people to the gallows, and given his personality, this must have been a rather uncomfortable thing for some of his rivals.
Oh yes, that don't want to be sent to the gallows by Isaac Newton, I can imagine at the time. But so who are some of Isaac Newton's students? Did he have any students? People who came immediately after him and built on his works?
He didn't have students per se, people he mentored, because he was much more of a loner. On the other hand, he inspired a generation of scientists. And in fact, really, the whole history of science since Isaac Newton is different from before. To give an example, though, of this, mathematicians in those days would pose challenges to each other. They would say, hey, here's a problem, see if you can solve it. So there's one famous problem that was posed by one of the Bernoullis, who were good mathematicians. And Newton, who was in his 50s at the time, thought about this problem, solved it on his long walk home, and sent in the solution anonymously. But when the person who had posed the problem saw this anonymous solution, he immediately said, "This is Newton. I recognize the lion by his paw."
That's very, and you don't, I think that would be something that, people just don't know about the man or his discipline and where he came from, a little bit of color about his life. I want to go to you, Race, and ask, maybe it's not a book about Isaac Newton, but maybe it's a book that you think would be interesting for people to read that tells them a little bit about photonics and everyday applications to their lives.
No, there are no really good books out there, so I would suggest Wikipedia.
Wikipedia?
Yes. Actually, it's I know a lot of people attract from it, but the information, especially among some of the more esoteric sciences, is really very good. So if you want to learn about photonics, hit there. Okay. I can throw a book at you, and it would probably be in German, and you would have to learn how to learn German before you could actually read it, because a lot of the radiometry was done in Germany. So there aren't any really good books on it. In fact, when I went to school, a lot of textbooks were carbon copies of other books that were no longer in print.
So you're one of the few experts in our area in this area?
No, there's quite a number of us, but radiometry is a big field and imaging science is a big field. But for books for the layman, there really aren't that many out there. So I'd say just go to Wikipedia and and Google some things, and you'll find out more information you probably could from any book I can tell you about.
Okay. So are there any final thoughts that you'd like to give us on Newton and the importance of his work on modern science?
To me, even beyond his remarkable specific contributions, the main thing is that Newton and some of his predecessors like Galileo and Kepler really ushered in the scientific way of thought. It's a way of trying to look at the universe, ask questions, pose it in ways that can be answered, and if you've answered a question, you go on to the next questions. You never have the final answer. You're always pushing and prodding for a greater depth of understanding. This, I think, is, in some sense, the largest legacy of Newton.
Well, thank you so much. This has been so great. We have been talking to Dr. Cole Miller and Mr. Race Dowling concerning the scientific contributions of Sir Isaac Newton. You can see more Scholars Chair on the Read One Communication YouTube channel. You can also follow us on Facebook. And if you want to email us, go ahead and send an email to scholarschair@gmail.com. I'm Maya Harris. Thanks and good night.
Hit it, hit it, hit it.
Amazing. This is the moment I knew. His future had no boundaries.
There are some moments only the forest can inspire.